in the next 60 seconds, while you lie perfectly still. Earth's orbit alone will carry you more than 1,000 miles around the sun. You will not feel a single mile of it. Beneath your bed, the ground is turning. Around that turning planet, the moon is drifting slowly outward. And, far above, our entire galaxy is wheeling through the dark, taking you with it. Almost nothing in the universe simply sits still. Tonight, we are going to ask the quiet question hiding behind all of it. Why? Why does so much of the cosmos spin? Planets, storms, dead stars, whole galaxies. The answer is a story about memory, about something the universe cannot throw away once it has been given. And it begins before the sun existed. You do not need to remember anything tonight. There is no test at the end of this journey. Just settle in, let your shoulders sink, and let the turning world carry you, the way it has carried every sleeper who ever lived. Let us begin. Before we visit a black hole, or a dying star, or the birth of the solar system, I want to begin somewhere much closer. I want to begin with you, exactly where you are. Maybe you are lying in bed, maybe you are on a couch, or in a chair by a window, or somewhere dim and comfortable with this playing softly nearby. Wherever you are, notice how still everything feels. The pillow is not moving. The walls are not moving. If someone asked you right now whether you are traveling or at rest, the honest answer from your body would be immediate and certain. I am still. I am not going anywhere. And here is the first surprise of the night. That feeling, that deep bodily certainty of rest, is one of the oldest and most convincing illusions a human being can have. Not a foolish mistake, a beautiful one. And it took our species thousands of years to see through it. Let me show you what is actually happening, one layer at a time. The first layer is the turning of the Earth itself. Our planet rotates completely around once a day, and that is where day and night come from. The one rhythm your entire life has been built on. But a full turn every day means the surface has a great deal of ground to cover. At the equator, where the circle is widest, the land sweeps along at roughly 1,000 miles per hour. Farther north, where most people in the United States and Europe live, the circle is smaller and the ride is a little slower, somewhere in the range of 700 to 800 miles per hour across most of the continental United States. Easing further as you travel toward the top of Europe. Either way, the quiet room you are resting in is moving faster than a passenger jet at full cruise. The second layer is larger. That entire spinning planet, with you aboard, is also traveling around the sun, and that journey takes a year. To complete it, the Earth moves at about 67,000 miles per hour. In the time it took you to arrange the blanket tonight and settle your head into the pillow, you covered 1,000 miles of that orbit and never noticed. Not as a metaphor, as plain, measurable fact. And there is a third layer still. The sun is one star among hundreds of billions, all of them circling the center of the Milky Way. And our sun carries the Earth around that distant center at roughly 500,000 miles per hour. Even at that speed, one single lap takes more than 200 million years. We will return to that enormous journey late tonight, when your thoughts are softer and big numbers can simply wash over you. So here is where you truly are, lying on a planet that turns. while it races around a star. While that star sweeps through a galaxy, stillness was never really on the menu. There are only speeds, stacked inside other speeds, all of them silent, which raises the honest question this chapter exists to answer. If all of that is happening, why can you not feel any of it? The answer is one of my favorite ideas in physics, and it is simple enough to hold in one sleepy hand. Your body is not built to detect smooth, steady motion. It is built to detect change. Deep inside each of your ears, there is a set of small fluid-filled canals, and they are exquisitely good at sensing when your motion shifts. Speed up, slow down, tilt, turn a corner, and they report it instantly, but hold a constant speed in a constant direction. And they fall quiet, because there is nothing new to say. You already know this from ordinary life, even if you have never named it. Think of an airplane at cruising altitude, 500 miles per hour, above the clouds. The flight attendant pours coffee. Someone walks down the aisle. A person 2 rows ahead is asleep with a magazine open on their chest. Nothing about the experience feels like speed. Then the plane hits a patch of rough air, and everyone feels it at once. Because turbulence is change, and change is the one thing the body was designed to catch. Now scale that up. The Earth's rotation is remarkably steady. It does not lurch or break. In truth, its rate does drift by tiny amounts, nudged by tides, by winds, by the slow rearrangement of the planet's own mass. And later tonight, we will measure that drift together and find something rather moving inside it. But those changes are far too small and far too gradual for any body to sense. Everything near you is moving with you at the same speed, in the same direction. The air in the room, the oceans, the clouds, your bed, your street, the trees outside. There is nothing nearby standing still for your senses to compare against. So the body reports the only thing it can honestly report: all quiet, nothing moving here. There is something genuinely comforting in that, and I offer it as the first small gift of the night. The reason you feel still is not that the universe is hiding something from you. It is that the ride is extraordinarily smooth. You are aboard a vehicle that has been making its daily turn for more than 4 billion years. So evenly that its passengers spent nearly all of history never suspecting they were passengers at all. But that smoothness came at a cost. And the cost was confusion. For most of recorded history, nearly everyone concluded that the Earth stood fixed while the entire sky wheeled around it. And honestly, who could blame them? Every night, the stars rose in the east and set in the west. The sun crossed overhead like a lamp carried slowly across a ceiling. The explanation that matched every feeling in the human body was that we are the still point, and everything else turns around us. It was a reasonable conclusion. It was also backward. The turning was ours all along. The sky only appears to wheel because we wheel beneath it. The way the countryside seems to slide past the window of a smoothly moving train while you sit perfectly comfortable in your seat, in no doubt at all about who is moving. Notice what this means, because it is the thread we will follow all night. The spin was always there. It was there long before anyone noticed it. Before telescopes, before language, before anyone at all. What changed, slowly and with great difficulty, was our ability to see it. And seeing it required something strange and admirable. It required people willing to trust careful reasoning over the direct testimony of their own bodies. People who could stand under that turning sky and think, what if the stillness I feel is the illusion, and the motion I cannot feel is the truth? For centuries, the evidence for a turning Earth accumulated in the sky, in the mathematics of planetary orbits, in measurements that only specialists could make and only specialists could check. All of it asked ordinary people to take the astronomers at their word. What was still missing was something anyone could witness. A demonstration, inside a single room, that would let an ordinary crowd watch their own planet rotate with their own eyes. That demonstration finally arrived in the winter of 1851. In Paris, it required no telescope and no mathematics, only a wire, a heavy weight, and a great deal of patience. Paris, the winter of 1851. Inside a grand domed building called the Pantheon, a crowd has gathered for something no audience anywhere has ever been promised before. A physicist named Léon Foucault has hung a brass-covered weight, about 60 pounds of it, from a steel wire fixed to the top of the dome, more than 200 feet above the marble floor. The weight hangs at the bottom of that long wire like a slow heartbeat waiting to begin. Foucault's public invitation contained a single remarkable line. He promised that those who came would see the earth turn, not hear an argument for it. See it. Before we watch what happened, drift backward with me for a moment, because the weight of this scene comes entirely from the centuries standing behind it. The idea of a turning earth is far older than most people expect. More than 2,000 years ago, the Greek astronomer Aristarchus proposed that the earth spins on its axis and travels around the sun. His reward, broadly speaking, was to be politely set aside for many centuries, not because his colleagues were fools, but because his idea collided head-on with the illusion we explored in our first chapter. Every human body on the planet testified, daily, that the ground was still. The idea returned in force in the 1540s, when the Polish astronomer Nicolaus Copernicus published a book placing the sun at the center, with the earth spinning daily and circling yearly. He had worked on it for decades and released it only at the end of his life. By most accounts, a finished copy reached him around the day he died. In 1543, he proposed the turning earth, and then left the room before the long argument even began. And it was a long argument, with thoughtful people on both sides. The skeptics had real objections, and they deserve to be heard properly. If the earth spins eastward at hundreds of miles per hour, they asked, why does a stone dropped from a tower land at its base instead of far to one side? Why does a bird that lets go of a branch not find its tree racing away beneath it? Why is there not a permanent gale howling from the east, day and night, everywhere on earth? Those are good questions. If you did not know the answer, they might convince you too. And the answer is the one you already own from chapter 1. The stone, the bird, the air, and the tower are all moving with the earth, together. So, the fall unfolds exactly as if nothing were moving at all. Steady, shared motion hides itself perfectly. The skeptics were not wrong about what they observed. They were missing one quiet principle underneath what they observed. Over the following centuries, the case for a turning earth grew from strong to overwhelming. Galileo found 4 moons circling Jupiter, proof that not everything in the heavens goes around us. In the 1690s, careful measurement showed that the Earth is not a perfect sphere, but bulges slightly at its equator, exactly as a spinning body should. In the 1720s, the English astronomer James Bradley discovered a tiny annual shift in the apparent positions of stars, an effect that makes sense only if the Earth is genuinely moving through space. Experimenters even dropped weights down deep mine shafts, hunting for the faint eastward drift a rotating planet should produce, and found hints of it. By the 1800s, essentially, every working scientist accepted the spin. But notice what all that evidence had in common. It was indirect, technical, assembled from measurements most people would never make, and mathematics most people would never read. The most basic fact about our own planet remained something ordinary people were asked to accept on authority. What was missing was not proof. What was missing was an experience. That is what Léon Foucault created. And the idea behind it is simple enough to carry into sleep. A pendulum, once set swinging, tends to keep swinging in the same direction, left alone, free from twists and side pushes. The plane of its swing holds steady while the world does whatever the world does. So Foucault reasoned that if you hang a pendulum carefully enough and let it swing long enough, the Earth will slowly rotate underneath it. To anyone standing on the floor, turning with the planet and feeling nothing, the swing would appear to drift, hour by hour, tracing out the rotation that no body can feel. Under the dome, the heavy weight was drawn to one side and held there by a cord, to begin the swing in perfect purity, with no sideways nudge from a human hand. The cord was burned through with a flame. The weight was released by fire, not fingers, and the great pendulum began its slow arcs, each one taking about 16 seconds, with a fine point beneath it, tracing its path through a ring of sand spread on the floor. Then the crowd did the hardest thing there is to do in science. They waited. If you like, wait with them a moment. Let your breathing take up the pendulum's unhurried rhythm. Out and back. Out and back. 16 seconds to an arc, with nothing to do but watch a heavy thing swing. And within the hour, there it was. The line traced in the sand had shifted. The swing was faithfully holding its direction. And the floor, the crowd, the dome, and the entire city of Paris had rotated slightly beneath it. People reportedly fell silent. Some said afterward that for the first time in their lives, they could feel, almost physically, that they were standing on something that moves. There is a detail here that I find quietly perfect, and it is worth knowing. The pendulum does not drift at the same rate everywhere on Earth. Directly over the North or South Pole, it would trace a complete circle in about a day, matching the planet's turn exactly. At the equator, it would not drift at all. Paris sits between those extremes. So its pendulum needed a little over 30 hours to come full circle. The instrument does not merely announce that the Earth rotates. It quietly reports your latitude while it does so. I want to linger inside that moment, because it may be the most moving scene in the history of knowledge. Nothing in the room changed. No new force appeared. No hidden machinery. The Earth had been turning beneath every pendulum, every swinging lamp, every child on every swing, for its entire existence. All Foucault did was arrange the conditions carefully enough for the truth to become visible, and then step back and let people look. The demonstration was so clear and so democratic that copies appeared in cities across Europe and America within months. To this day, more than 170 years later, Foucault pendulums swing in museums and universities around the world. In Paris, in Chicago, in New York, still performing the same patient, proof for anyone willing to stand and watch. The following year, Foucault built another instrument to show the same thing a second way. A spinning wheel mounted so it could hold its orientation freely. He gave it a name we still use. He called it the gyroscope. Here is the lesson folded inside the story. And we will carry it all night. The spin of the earth was never hiding. It was simply steady. And steadiness is invisible to creatures built to notice change. It took a wire, a weight, and an afternoon of patience to make the invisible visible. Again and again tonight. We will watch this pattern repeat. Spin is everywhere, ancien and constant. And the history of astronomy is largely the history of learning. One clever trick at a time. How to see it. But the pendulum only shows that the earth turns. It says nothing about the deeper question, the one this entire night is really about. Why does it turn? Where did the turning come from in the first place? And why should a planet be turning at all? The answer begins, of all places, on a sheet of ice, with a single figure skater, arms outstretched, beginning to spin. Picture an ice rink. Late in the evening, nearly empty, the lights are low, and the ice has that soft shine it gets after hours of gliding blades. One skater remains, finishing her practice. She glides to the center, plants her two, and begins to turn. Slowly at first, arms stretched wide, like a door swinging easily on its hinge. Then she pulls her arms in, folding them against her chest, and instantly, without any extra push, she becomes a blur. Her lazy turn leaps into a whirl the eye can barely follow. Then she opens her arms again, and just as smoothly, the whirl relaxes back into that slow, graceful turning. You have seen this at the Olympics, in a film, perhaps at a local rink on a winter afternoon. It is so familiar that it is easy to miss the question a physicist cannot help asking. Where did the extra speed come from? Nobody pushed her. She did not take another stroke against the ice. She simply moved her own arms closer to her own body. And the universe answered by turning her faster. That small mystery on the ice holds the key to our entire night. So let us open it slowly, because this is the one piece of physics I truly want you to carry with you. And it is gentle enough to fall asleep holding. The principle is called the conservation of angular momentum. And I promise the name is the most complicated thing about it. Here is the bedtime translation. Anything that is turning carries a certain amount of turning. Not a metaphor, a real and measurable quantity. For a simple, solid object rotating on an axis, that quantity depends on two things: how fast it turns, and how far its mass sits from the center of the turn. Physicists have a name for that second part: the way an object's mass is arranged around its axis. They call it the moment of inertia, and when they multiply it by the rate of turning, they get the amount of spin the object carries. And the deep rule, tested in laboratories, confirmed in the motions of planets, never once observed to fail, is this: in a system left to itself, that amount cannot change. Spin cannot be conjured out of nothing, and it cannot simply evaporate. It can only be passed along, traded, handed off to something else. It is conserved. The books must always balance. Now watch the skater again with that rule in mind. Arms out. Her mass is spread wide. Her moment of inertia is large. So, a slow turn is enough to carry the amount of spin she has. Arms in. Her mass gathers close to the axis, and her moment of inertia drops sharply. But the total she carries is not permitted to drop with it. So the only thing left that can change does. Her rate of turning rises. Immediately and automatically, by exactly enough to keep the total the same. She is not creating spin when she pulls her arms in. She is concentrating it, and here is the crucial piece of fine print. The sentence, "this whole night rests on." So let it settle in slowly. Pulling her arms in only works because she was already turning. If she stood on the ice perfectly motionless and pulled her arms in, absolutely nothing would happen. No spin appears from nowhere. Contraction does not create rotation. What contraction does, and does spectacularly, is amplify rotation that already exists. A turn too slow to notice can become, through shrinking alone, a turn too fast to follow. The whisper becomes a roar. But there has to be a whisper to begin with. You can see the same rule everywhere. Once you know its face, a diver leaves the board with a slow tumble, tucks into a tight ball, and fits 3 somersaults into the fall. A cat dropped gently from a safe height twists its flexible body in midair, trading spin between its front and back halves so precisely that it lands upright. None of them is inventing motion. Each is rearranging what it already had. Glide with that thought for a moment. The way a skater glides between moves, letting the ice do the work. So the honest question becomes, where do the whispers come from? Why do the objects of the universe so reliably carry at least a little rotation before anything begins to shrink? Part of the answer is that spin is easy to acquire and remarkably hard to erase. The universe is a crowded, busy place, and its contents are forever tugging at one another, colliding, brushing past, tearing material loose. Almost any interaction that is even slightly off-center leaves the participants turning. One twisting one way, the other twisting back, the totals still balancing. It is very difficult to touch something in this universe without setting it spinning a little, and once a thing carries rotation, getting rid of it is genuinely hard. You cannot simply delete it. It has to be handed to something else, carried off by escaping material, or slowly transferred through long, patient tugging. That single fact will follow us through every chapter tonight, and much later. When your thoughts have gone soft, it will turn out to be the real answer to the question printed on this journey. Spin is a debt the universe cannot cancel. It can only pass it along. The other part of the answer is simply what we observe when we look. When astronomers study the vast clouds of gas drifting between the stars, the raw material that worlds are made from, they find them stirred and turbulent, rippled by the winds of nearby stars, tugged by neighbors, churning internally in every direction at once. Within a large cloud, some regions lean one way and some the other. But take almost any particular pocket of such a cloud, the kind of pocket that might one day collapse into a star, and the churning inside it almost never adds up to exactly nothing. Some slight overall drift is nearly always left over, not because stillness is forbidden, and not because there is some law against it, but because in a place this stirred and this interconnected, an exactly cancelled leftover is simply not what the churning tends to produce. Now lay the two ideas side by side. Like puzzle pieces on a quiet table, real clouds, as we actually find them, almost always carry at least a faint whisper of overall rotation. And whenever such a cloud collapses, gravity drawing it inward, the skater's law takes over, and the whisper is amplified enormously, automatically, with no engine and no push required. A drift so slow that a single turn would take 1,000,000 years can become, through collapse alone, a rotation measured in days, or in hours, or, as we will see deep in the night, in fractions of a single second. That is the secret the skater has been performing in plain sight all along. The universe does not conjure spin from nowhere. It inherits spin, passes it along, and wherever gravity gathers things inward, concentrates it beyond all recognition. Which brings us to the edge of a story 4.5 billion years old. A cloud of cold gas and dust, wider than anything you have ever pictured, drifting in the dark between the stars, already carrying its faint, invisible turn. It had drifted that way for ages. It might have drifted that way far longer, and then something disturbed it, and the long fall began, the fall that would become the sun, the fall that would become the earth, the fall whose leftover turning you have felt as every single morning of your life. 4.5 billion years ago, there was no sun, no earth, no morning, no night, no sky as you know it. In the place where our solar system now sits, there was only a cloud. Picture it loosely, without straining, because no picture can really hold it. A cloud of gas and dust hovering only a few degrees above the coldest temperature physics allows, and so wide that light itself would need years to cross it. Mostly hydrogen, the oldest and simplest ingredient in the universe, salted with fine grains of dust, tiny flecks of carbon and silicon and ice, each one smaller than the width of a hair. Astronomers call these structures molecular clouds, and our telescopes can see thousands of them tonight, scattered through the galaxy, dark and patient, like fog drifting between streetlights. And our cloud, the one that would become everything you have ever touched, was already doing something. It was turning, imperceptibly. Its rotation was the whisper from the last chapter, the faint leftover of every ripple and tug and near miss it had experienced across its long life, summed into a drift so slow that a single turn might have outlasted the entire history of complex life on Earth. For a long stretch of time, perhaps millions of years, Revose, the cloud simply hung there, balanced, its own gravity pulled inward, the pressure of its gas pushed outward. The two leaned against each other like tired dancers, and nothing much happened. Then something broke the balance. Here, the record goes quiet, and I would rather tell you that plainly than pretend otherwise. No one knows for certain what tipped this particular cloud into collapse. The event left only fingerprints, not a signature, but the fingerprints are real, and one of them is remarkable enough to be worth your attention. Locked inside certain meteorites, the oldest surviving objects in the solar system, Researchers have found the decay products of short-lived radioactive atoms, atoms with lifetimes so brief that they must have been created shortly before the solar system formed, then swept into the material that built it. One of the few things in nature capable of forging such atoms is a massive star reaching the violent end of its life. So, the evidence points clearly to a dramatic stellar neighbor, seeding our cloud with freshly made material. But notice exactly what that does and does not tell us. The isotopes prove the neighbor existed. They do not record what pulled the trigger. One possibility, actively studied, is that the blast wave from that dying star also squeezed our cloud and helped tip it into collapse. Another is that the cloud was compressed as it drifted through a spiral arm of the galaxy, or jostled by a collision with another cloud, or that it simply cooled and grew heavy enough that its own gravity finally won on its own schedule. The fingerprints tell us the neighborhood was lively. They do not preserve the moment of the push. Whatever the cause, the balance tipped. In one dense pocket, gravity won, and the long fall began. Let the fall itself set your pace here. Not a plunge, but a settling, the way snow comes down on a windless night. Unhurried, in no doubt about where it is going, the pocket collapsed inward. Atom drawn toward atom, the fall feeding on itself. Because the denser the center grew, the stronger its pull became. And now everything from the ice rink comes home. This pocket was the skater. Arms stretched impossibly wide, already carrying its faint whisper of rotation. As it fell inward, shrinking from a span of trillions of miles toward a span of mere millions. That whisper was amplified. The books must balance. The mass was gathering close to the axis, so the rate of turning had to rise. A turn that once took ages tightened, era into a turn taking millennia, then centuries, then years. Nothing spun the cloud. The cloud concentrated a spin it already owned, exactly as the skater does, on a scale a billion times larger. And that amplified rotation reshaped the fall itself. Here is the part I find most beautiful, and it is the answer to this chapter's title. The cloud could not send all of its material straight to the center, because it was already turning before it began to fall. Material drifting in from directly above and below, along the axis of that turn, met nothing to hold it up, and fell freely inward. But material coming in from around the middle was carrying the cloud's rotation with it, sweeping sideways as it fell. And the faster the rotation grew, the harder that material found it to complete the last part of the journey. It did not fall to the center. It fell into orbit around the center. So the collapsing sphere flattened, steadily, like dough spun in a baker's hands, thinning at the poles, spreading at the waist, until what remained was a vast, turning disk of gas and dust with a swelling, brightening mass at its heart. Astronomers call this a protoplanetary disk, and here is one of my favorite facts of the modern era. This is no longer only a story we tell. We have photographed it. In 2014, a telescope array high in the Chilean desert called ALMA captured an image of a very young star named HL Tauri, a few hundred light years away, and the picture showed exactly this: a smooth, glowing disk of dust wrapped around a newborn star, complete with dark rings where new planets appear to be sweeping their lanes clean. The image resembled the old textbook diagrams so closely that it startled even professional astronomers. A real nursery, caught in the act. A portrait of what our own home looked like before it had a name. At the center of our own disk, the falling gas piled deeper and hotter, until the core finally reached the pressure and temperature where hydrogen begins fusing into helium, and a new kind of fire switched on, the kind that can burn steadily for 10 billion years. The sun had begun, and the sun gathered nearly everything. More than 99% of all the material in the solar system, by mass, sits in the sun today. The planets, the moons, the asteroids, the comets, every mountain and ocean and sleeping person on Earth. All of it together amounts to less than 1%. The crumbs left circling the table after the meal. But those crumbs inherited something precious. Every scrap of leftover material was already in motion, circling the newborn sun in the same direction, in nearly the same flat plane, each piece carrying its share of that original, amplified whisper. Hold that softly as this chapter closes, because it answers a question you have never needed to ask. Why does the sun rise every morning? Not the poetic answer, the physical one. The sun rises because the earth turns, and the earth turns because it was assembled out of a disk that was already turning, and that disk was turning because a cloud too vast to imagine was already, faintly, turning before it ever began to fall. Tomorrow's light through your window will be, in the most literal sense, the continuation of a motion older than the sun itself. Dawn is the oldest heirloom you own, and if every planet was built from that one turning disk, then all of them should carry a family resemblance, a signature written across the whole solar system. They do, almost. Let us look through the family album slowly, the way you might on an evening with nowhere to be. 8 planets circle the sun: Mercury, Venus, Earth, and Mars. The 4 small rocky worlds of the inner system, then Jupiter, Saturn, Uranus, and Neptune. The 4 giants of the outer dark, 8 worlds with wildly different faces. One scorched bare by its nearness to the sun, one smothered in golden acid clouds, one covered in oceans and forests and sleeping cities, one rusted red and silent, one large enough to swallow all the others combined, one wearing rings like a piece of jewelry, and beneath all that variety, the family resemblance is unmistakable. Once you know where to look, start with the shape of the whole system. The planets do not swarm around the sun at every possible angle, the way moths circle a porch light. They travel in very nearly a single flat plane, like grooves on a vinyl record, shrink the entire solar system down to the size of a dinner plate, and the orbits of all 8 planets would lie very nearly within the thickness of the plate itself, with only slight tilts separating one from another. You can see this ancient flatness with your own eyes. Tonight, or any clear night, with no equipment at all, the sun, the moon, and the visible planets all cross our sky along very nearly the same line. If you have ever noticed the moon sitting close to a bright planet, or watched the full moon rise at the same point on the horizon where the sun set months earlier, you have been reading that line without knowing it. It has a name, the ecliptic, and it is the edge of the ancient disk, seen from inside it. Now watch the direction of travel. All 8 planets orbit the sun the same way. Seen from high above the sun's north pole, Every single one moves counterclockwise. There are no exceptions among the planets. 8 worlds. One direction. The direction the original disk was turning. This part of the inheritance, the shared plane and the shared direction of travel, is the solid, uncontested heart of the story. It falls straight out of the physics of a collapsing, flattening, rotating cloud, and it is exactly what we find when we look. In recent decades, the story has grown larger than our own neighborhood. Since the mid-1990s, astronomers have discovered thousands of planets orbiting other stars. And in system after system, the same broad architecture appears. Planets in flat planes, planets sharing a direction of travel, generally aligned with the turning of their own star. Other disks, other falls, other families. It is not a perfect rule out there, and the exceptions are among the most interesting objects in the sky. Some giant planets orbiting scorchingly close to their stars travel on strongly tilted paths, and a few move backward around their stars entirely, against the direction the star itself spins. Nobody thinks those worlds were born that way. They are read as evidence of rough lives after birth, of gravitational shoving matches with sibling planets, or of long, slow tugging by a distant companion star, which is a rather wonderful thing to be able to say. When a planetary system breaks the pattern, we can often tell that something happened to it. Then there is the third layer of the resemblance. And this is where I want to slow down and be more careful than the tidy version of this story usually is. The spins. The sun rotates counterclockwise, the same direction the planets travel. Mercury spins counterclockwise. So do Earth and Mars, and Jupiter and Saturn and Neptune. Most of the family turns the same way it travels, like dancers circling a room, while each also turns in the direction of the circling. But why a planet spins on its own axis is a messier and more individual question than why it orbits the way it does. The orbits we understand solidly, they were set by the disk. A planet's own spin, though, is the sum of a long and complicated childhood. Each world was assembled from countless collisions, and the final twist it ends up with depends on the detailed history of how its pieces arrived. The swirling of the gas it grew inside, the handful of enormous impacts it absorbed late in its formation, and everything that has tugged at it in the 4.5 billion years since. The turning disk stacked the odds in favor of spinning in the family direction, and most of the planets do. But a planet's spin is less like an inheritance certificate and more like a signature, shaped by everything that ever happened to the hand that wrote it, which means the spins are not merely leftovers. They are records. Read a planet's spin closely enough, and you are reading its biography. Let the album rest open on your chest for a moment. There is no need to turn the page just yet, because when you do read those biographies, 6 of them tell roughly the same family story, and 2 of them do not. 2 members of this family carry spins so strange that they demand some private chapter the others never lived through. Taken together, those 2 exceptions may teach us more about what spin really is than all 6 well-behaved siblings combined. One of them lies fully on its side, rolling around the sun like a barrel. Its seasons stretched across decades. We will visit that one soon, but first, the nearer rebel, the brightest planet in our sky, wrapped in golden cloud, where a single turn on its axis takes longer than an entire year, and where the sun, for anyone who could somehow see it through that sky, would rise in the wrong place entirely. Something happened to Venus. If you have ever stepped outside just after sunset and noticed a single light in the west far brighter than everything else, steady where the stars are twinkling, then you have already met Venus. People sometimes take it for an airplane, or report it as something stranger. It is simply the world next door, one of Earth's nearest planetary neighbors, wrapped in a permanent blanket of pale golden clouds that reflect sunlight like polished metal. In all our night sky, only the moon outshines it. Venus has been watched for as long as there have been watchers. Babylonian astronomers tracked its appearances and disappearances with great care thousands of years ago, and for most of history, it was imagined as Earth's twin, which was a perfectly reasonable guess. Venus is almost exactly the size of Earth. It has nearly the same mass, built of similar rock, formed in the same disk at a similar distance from the same young sun. If you had surveyed the newborn solar system and been asked which two worlds would grow up most alike, you would have pointed at those two without hesitating. And yet, for centuries, no one could see the surface, because those beautiful clouds never part. Not once, anywhere, at any time. The planet is sealed, so astronomers could not watch a mountain or a crater carry itself around and clock the rotation, the way you can with Mars. Deep into the 20th century, the spin of the brightest planet in our sky remained an open mystery. Some suspected it turned in about a day, like Earth. Others thought it might keep one face permanently toward the sun. The answer finally arrived in the early 1960s. And it came not from looking, but from listening. Scientists, including a team at NASA's Jet Propulsion Laboratory, bounced radar signals off Venus, straight through the clouds, and read the faint echoes that returned. A spinning surface stretches and squeezes a reflected signal in a measurable way. And from that stretching, the rotation can be read. When the results settled, they were strange enough that they took real convincing. Venus barely spins at all, measured against the distant stars. One full rotation takes about 243 Earth days, the slowest turn of any planet in the solar system. Meanwhile, its year, one full trip around the Sun, takes about 225 Earth days. Read those two numbers together, and the strangeness lands. The planet finishes an entire orbit before it finishes a single rotation, and because the slow spin and the orbital motion combine, the cycle of daylight there works out to something else again. From one sunrise to the next, on Venus, is roughly 117 Earth days, nearly 4 months of daylight, then nearly 4 months of night, over and over, forever. However you choose to measure it, time on Venus moves like honey. That was only half the surprise. The radar carried a second message. Venus turns backward, seen from high above the solar system, where every planet orbits counterclockwise, and 6 of the 8 also spin counterclockwise. Venus rotates clockwise, against the flow, against the memory of the disk. Astronomers call this retrograde rotation, and it means the geometry of morning there is reversed. On Venus, the sun would rise in the west and set in the east, crawling across the sky over the better part of 2 months. Every sunrise you have ever watched came up in the east because of the inheritance we traced across the last 2 chapters. Venus is the world next door where that inheritance runs in reverse. So what happened to it? Honestly, This is a case that remains open. Whatever occurred lies billions of years in the past and left no witnesses. But scientists have narrowed the field to a few serious storylines. And each is a different kind of biography. The first is the dramatic one, a giant impact. The young solar system was crowded with leftover planet-sized bodies, and enormous collisions were simply part of growing up, as we will see again in a moment when we reach Uranus. In this picture, Venus was struck early, hard, and at just the wrong angle, and the blow either flipped the planet over or nearly cancelled its original spin and left it drifting slowly the other way. It is possible. Worlds were certainly being hit that hard in those days, but a blow of that scale might well have left other traces. Perhaps a moon, like the one a giant collision is thought to have given Earth. Venus has no moon at all. The impact story stays on the table without being the favourite. The second storyline is slower, stranger, and needs no collision whatsoever. The air on Venus is nothing like our air. It is a crushing ocean of carbon dioxide, roughly 90 times the pressure of Earth's atmosphere, so dense near the ground that it behaves almost like a fluid sea. The sun raises tides in that immense atmosphere, and the sun's heat drives great daily waves through it. And an atmosphere that massive, sloshing age after age, pushes back on the planet beneath it. In this picture, the forces acting on Venus became a long tug of war. Tides raised in the solid body of the planet worked to slow it and lock it toward the sun, while the powerful heat-driven tides in that thick atmosphere pushed in the opposite sense. And across billions of years, the planet's spin was worn down and reshaped by the contest between them. Several versions of this story have been modelled in detail. In some, Venus was slowed, stalled, and eased into a gentle backward drift. In others, the planet tipped over entirely somewhere along the way. More than one version fits what we can measure today, and that is precisely the difficulty. So the case stays open, and I want to say clearly what that means, because it may be the most valuable thing this chapter has to offer. The backward spin is real, measured, and beyond doubt. The explanation for it is unfinished, actively studied, and genuinely uncertain. Both of those sentences are true at the same time, and holding them together comfortably, without forcing a verdict, is what working science actually feels like from the inside. New missions to Venus are being planned by NASA and the European Space Agency with exactly these questions in view. Before we leave, one careful separation, because it matters. Venus today is the hottest planet in the solar system, hotter even than Mercury, which sits far closer to the Sun. Its surface bakes at around 900 degrees Fahrenheit beneath that crushing sky, hot enough to melt lead. The hardiest Soviet probes that landed there in the 1970s and 80s survived. At best, around 2 hours before the heat and pressure silenced them. That furnace is not the fault of the slow spin. It is a separate story, driven overwhelmingly by that enormous blanket of carbon dioxide trapping heat that cannot escape. What the strange spin does shape is the rhythm of the place. Its 4-month days and 4-month nights. The sluggish way its deep atmosphere circulates. The odd fact that its high clouds race around the planet far faster than the ground below them ever turns. Two different mysteries, living on the same world, and it is worth keeping them apart. Carry this out of the chapter. Wrapped soft. A spin can be rewritten, not only by catastrophe, but by patience, by tides and sunlight leaning on a world for 1 billion years until its days run backward. Venus, for all its strangeness, at least still stands roughly upright. Its rebellion is in the direction of its turning. Far out in the cold, there is a world whose rebellion is the opposite. Its turning is perfectly ordinary. Its posture is not. Out here, the sun has become small, stunned, in imagination. In the cloud tops of Uranus, nearly 2 billion miles from home, and the sun is no longer the warm disk, you know. It is a brilliant point among the stars, delivering nearly 400 times less light than falls on Earth. Noon here is dimmer than a heavily overcast evening at home. This is the 4th largest planet in the solar system, an ice giant about 4 times the width of Earth, colored a soft, even, blue-green calm by traces of methane in its cold upper air. Uranus holds a particular place in tonight's story, and it is worth a short detour to say why. It was the first planet ever discovered. Every world closer to the sun has been known since before history. Bright and obvious to anyone who looks up, but Uranus is so distant and so dim that it waited until 1781, when the astronomer William Herschel, sweeping the sky with a telescope he had built himself, noticed a faint point of light that drifted slowly against the background stars over several nights. With that single observation, the known solar system doubled in size overnight. That was the first surprise Uranus offered. The second took far longer to reveal. And it is the reason this chapter exists. Every planet's spin axis tilts a little, measured against the plane of its orbit, and that tilt is one of the most consequential numbers a world can carry. Earth leans about 23.5 degrees, and that lean is the entire reason seasons exist. For half the year, the northern half tilts sunward and warms, while the south cools, and then the geometry swaps, and everything you associate with summer and winter follows from it. Mars leans about 25 degrees and has seasons much like ours, stretched across its longer year. Jupiter barely leans at all, roughly 3 degrees, and so it scarcely has seasons. Saturn and Neptune lean somewhere near Earth's angle, modest tilts, family tilts. Then astronomers measured Uranus, and the number refused to behave. Its axis is tilted about 98 degrees. Let that unfold into a picture. 90 degrees would mean lying fully on its side, its poles pointing along its orbit instead of up out of it. Uranus leans slightly past even that. It is not standing and turning like a top on a table, the way Earth does. It is lying down and rolling, like a barrel, around the sun, with one pole aimed nearly at the star for part of its orbit, and, decades later, the other. And because that lean passes 90 degrees, Uranus technically joins Venus in the backward spinning club, though the two rebellions could not look less alike. Venus stands upright and turns the wrong way. Uranus turns well enough and simply refuses to stand. Follow the consequences, because they are wonderful, and because they show again how a spin quietly writes a world's fate. Uranus takes 84 Earth years to circle the Sun, rolling on its side. Its seasons are like nothing else in the family. Its North Pole spends about 21 years angled toward the Sun, One unbroken, dim summer, decades long. While the south endures about 21 years of continuous night, then come 2 more long seasons closer to ordinary, when the sun stands over the equator and day trades with night in a familiar rhythm, before the whole cycle mirrors itself. There are places on that world where the sun rises once and sets once in the span of a human generation. If a season that long sounds exhausting, let it be the opposite. Somewhere out there is a world where a single night lasts 21 years, and it rests through all of them, and nothing about it is in any hurry. When Voyager 2 flew past in 1986, still the only spacecraft ever to visit, it found a planet almost eerily calm, a smooth blue face with barely a visible cloud. One pole pointed nearly at the sun, and the measurements held a gentle twist, despite one hemisphere soaking up decades of sunlight while the other froze in darkness. Temperatures across the planet turned out to be nearly even. The winds and the deep circulation quietly redistribute what little heat arrives. Even knocked over, the planet found its own equilibrium. But the question is the same one Venus forced on us. The disk builds upright worlds. Nothing in the calm settling of dust produces a giant lying on its side. So what happened here? Something appears to have tipped Uranus dramatically, and the leading suspect, studied in computer simulations by research groups around the world, is a collision. In the standard picture, the young Uranus was struck by a massive body, perhaps around twice the mass of Earth, one of the leftover worlds still wandering the chaotic early solar system. Hitting, not head-on, but at a glancing angle, a blow like that would not shatter a giant planet. Uranus is far too large for that. But delivered off-center, it could torque the entire world, wrenching its axis over in what amounts, cosmically speaking, to an afternoon. The evidence that makes many scientists favor this story is the planet's family. Uranus has rings and more than 24 known moons, and they do not orbit in the plane of the old solar system. They circle the planet's tilted equator, lying over right along with it, as though the whole household fell together. That is what you would expect if the moons formed out of debris splashed into orbit by the impact. After the tilt, and it is harder, though not impossible, to arrange if something tipped the planet slowly instead. Fairness requires the other side, though, and the other side is real. The impact models carry their own unsolved problems. From the difficulty of rebuilding that particular family of moons out of the debris, to the puzzle of why Uranus radiates so little internal heat, far less than a recently walloped planet might be expected to. Some researchers pursue gentler explanations instead, in which rhythmic gravitational nudges, resonances, built up patiently over long ages, perhaps involving a large moon Uranus has since lost, levered the planet over degree by degree. The tilt is a fact. The tipping is still a debate. Step back now and look at what these last 2 chapters have shown together, because they complete a thought that neither could finish alone. Venus and Uranus broke the same family rule in different ways, and their scars point to different kinds of history. Venus, if the tidal storyline holds, was changed gradually, worn into reversal, one whisper at a time, across billions of years. Uranus, if the impact storyline holds, was changed in a single day. By one blow it has carried, unhealed, ever since. erosion and catastrophe, the slow hand and the sudden one. Those are the two sculptors of everything in this universe. And here they are, displayed side by side in our own family, written in the spins of two worlds. So slip this under your pillow. A planet's spin is a document, one of the oldest a world possesses, recording the disk that built it and every insult, every break, every blow it has suffered since. Astronomers read spins the way historians read old letters. On 6 planets, the handwriting of the ancient disk is still legible. On 2, something scrawled across the page, and even the scrawl tells a story. So far tonight, though, every world has been a separate top, spinning or stumbling on its own. We have not yet watched what happens when two worlds hold each other closely for billions of years, each one's gravity working on the other without pause. Because spin, it turns out, is not a private possession. It can be traded. It can be given away. You do not have to travel far to watch it happening. You only have to look at the nearest object in the sky. Every night of your life, broadly, the same face has been watching you. Think of any moon you can remember. A summer moon over a lake. A cold moon behind bare branches. A huge orange moon rising over a highway at the end of a long drive. In every one of those memories, you were looking at essentially the same features, the same dark plains that people have read as a face, or a rabbit, or a pair of hands, the same bright highlands, the same familiar scatter of craters. Every painter who ever painted the moon, every sailor who ever steered by it, every child who ever pointed at it from a car window, saw the side you will see tonight. In truth, the moon rocks very slightly as it travels, a slow nodding and swaying that astronomers call libration, so that patient observers on Earth can peek a little way around its edges over time and glimpse, in total, about 59% of its surface. But the far side proper, the hidden heart of it, stayed hidden across the whole of human history. Nobody saw it. Nobody saw so much as a picture of it until 1959, when a small Soviet spacecraft called Luna 3 swung around behind the moon and radioed home the first grainy photographs of a landscape no eye had ever seen. And no human being looked at it directly until 1968, when the crew of Apollo 8 became the first people to fly around the moon and watch its far side pass beneath their window. Sit with the size of that for a moment. Our species looked up at that object for a couple of 100,000 years, and the other half of it entered human experience within living memory. So the question asks itself, why does the moon show us only one face? Is it simply not turning? Here is the gentle surprise. The moon is turning. It rotates on its axis like every world we have met tonight. But it rotates exactly once for every orbit it completes around the Earth. Once in about 27 days. And those two motions are matched so precisely that the same side faces us always. To feel it in your body rather than your head, imagine walking a slow circle around a chair while keeping your face toward it the whole way. By the time you arrive back where you started, you have turned completely around once. Anyone sitting in that chair, though, only ever saw your face. That is the moon's entire life. It turns, and its turning is exactly swallowed by its circling. A match that perfect should make you suspicious. Nature does not deal coincidences that clean. If the moon's spin ran even slightly fast or slightly slow, we would eventually see every side of it. Something enforced this. And that something is the main character of this chapter. A patient force that has been quietly editing the spins of worlds since the solar system began. The tide. You know the tide as the rise and fall of the sea. And the moon is famously responsible. But look one level deeper. The moon's gravity pulls hardest on the side of Earth facing it, a little less on the Earth's center, and less still on the far side. That difference stretches our planet very slightly along the line pointing at the moon. The oceans, being liquid, answer most visibly, gathering into two broad bulges. And as the Earth spins through them, your shoreline rises and falls. But the rock stretches too. The solid body of the Earth flexes by roughly a foot with every pass. A slow tide of stone that nobody feels. And the Earth does the same thing to the moon, far more powerfully, because the Earth is about 80 times more massive. In its youth, the moon was kneaded like dough, stretched and released, stretched and released. With every single rotation, that kneading costs something. Flex any material over and over, and it warms. And the energy has to come from somewhere. For the young moon, it came from the spin itself. Long ago, the moon almost certainly rotated faster, showing the young Earth all of its faces in turn. But every rotation dragged its tidal bulge around with it. And the Earth's gravity hauled back on that bulge like a hand gripping a spinning ball. And, across long ages, the extra rotation was worn away into heat. The turning slowed, and slowed, until the day matched the circling exactly. At that point, the stretching mostly settled into place, and the great breaking eased. Because there was so little left to break. Not nothing. Even now, the moon's orbit is slightly oval rather than perfectly round. Its gentle rocking continues, and faint tidal flexing still works on it. But the ancient fury of it is spent. Astronomers call the result tidal locking, and it is the universe's version of a long marriage. Two bodies, holding on, gradually wearing away every motion that pulls against the other, until what remains is effortless synchrony. And the story runs in the other direction too, which is where this chapter arrives at your own window. The moon is doing to the Earth precisely what the Earth did to the moon. Our tidal bulges run slightly ahead of the moon as our planet spins. The moon pulls back on them, and that pull is a brake resting gently on the Earth. Our planet's rotation is slowing. Across the ages, the days are growing longer. Before that unsettles anyone, here is the actual number, and it may be the most soothing number of the night. Records of ancient eclipses, combined with modern measurement, indicate that the day lengthens by roughly 0.02 of a second per century, 2 milliseconds, per 100 years. And even that is a long-term average rather than a steady march. From year to year, the length of the day wobbles by small amounts, nudged by winds and oceans and the churning of the planet's deep interior. Some years run a fraction slower, some a fraction faster, before the ancient trend reasserts itself over the long haul. You will live your entire life inside those flutterings and never feel one of them. But give the trend enough time and it moves mountains. The Earth keeps fossils of its own spin. Certain ancient corals and layered tidal sediments grew in daily and monthly rhythms, recording the calendar of vanished ages directly into their structure. And when researchers count those growth lines, the message is consistent. Hundreds of millions of years ago, the day appears to have been only around 22 hours long, and the year held closer to 400 days. The dinosaurs' days really were shorter than yours. Every creature that ever lived before us lived on a faster spinning world. And your own day, tonight, is among the longest this planet has ever offered any sleeper. One more piece. My favorite, because it closes the loop with the deepest rule we know. All that spin the earth is losing cannot simply vanish. The books must balance, and they do, gracefully. As the earth's rotation slows, the momentum it loses is transferred, through those same tidal bulges, into the moon's orbit, lifting it, easing it outward. The moon is drifting away from us. And this is not theory, but direct measurement. Because the Apollo astronauts left mirrored panels on the lunar surface, and for more than 50 years, observatories have bounced laser beams off them and timed the round trip to extraordinary precision. The verdict is exact. The moon recedes by about 1.5 inches every year, roughly the speed your fingernails grow. Nothing is lost in that exchange. Spin is leaving the Earth and arriving in the sky, converted into a slowly widening orbit. When you notice the moon tomorrow night, you can know something almost nobody looking up at it knows. You are watching where the length of our days is going. Let the tide set your rhythm as this chapter ebbs. Water breathing on a shore, arriving without effort, leaving without regret. 6 hours in and 6 hours out. Older than anything alive. If nothing else ever changed, the breaking would continue until, tens of billions of years from now, the Earth itself became locked, one face forever toward the moon. Day and month grown equal at last. The two of them frozen in a mutual gaze. It is a strangely tender final image, and one the universe will almost certainly never deliver. Because billions of years earlier, the sun will end its long middle age and swell, rewriting this entire neighborhood. The last dance of the earth and moon will be interrupted by the star that made them both possible. Which is the right door to leave through? All night we have treated the sun as the still anchor everything else circles around. But the sun turns too, and its turning is stranger than any planet's. Because the sun is not solid, and a spinning thing that is not solid can do something no planet can do. It can turn at several speeds at once. Here is a small experiment you will never be able to perform, and the impossibility of it is the whole point. Stand on the equator of the sun, and have a friend stand near its north pole. Wait for one full rotation. You will come back around to your starting point in about 25 days. Your friend will need about 35. Read that again. Slowly. 2 points on the same object, completing their circles at different rates. If the Earth attempted that, it would tear itself apart, because the Earth is rock, and rock must move together. A solid ball has one rotation rate. Everywhere. By definition, your city and the North Pole complete their daily circle in the same 24 hours. Always. Without exception, the sun is under no such obligation, because the sun is not solid. There is no surface there. Not really. Nothing you could stand on. Nothing you could plant a flag in. The sun is a sphere of plasma, gas so hot that its atoms have been torn into charged fragments. nearly 1 million miles across, held together by nothing but its own gravity, and a fluid body does not have to turn in one piece. The sun's equator laps its poles, endlessly, rotation after rotation, age after age. Astronomers call this differential rotation, and almost everything dramatic the sun does begins here. People have known the sun turns for about 4 centuries, and the way they found out is charming. In the early 1600s, observers, including Galileo, began projecting telescope images of the sun onto paper and tracking sunspots. The dark blemishes that drift across its face. The spots cross the disk over roughly 2 weeks, disappeared around the edge, and returned on schedule. The sun was plainly rotating. It took longer to notice the deeper oddity, that spots near the equator finished the journey faster than spots at higher latitudes. The sun was turning, and it was somehow out of step with itself. To feel why that matters, you need 2 more ingredients, and I will hand them over gently. The first is that plasma is not simply hot gas. Its particles carry electric charge, and charged material and magnetic fields are bound to one another. Where the plasma flows, the magnetic field is dragged along with it, frozen into the material like threads embedded in honey. Hold that image. Threads in honey, and you own half the key to solar physics. The second ingredient is that the outer third of the sun is boiling. Heat rising from the depths cannot simply radiate through that layer, so it moves the way heat moves in a pot of soup, in enormous convection cells. Hot plasma climbs, spreads across the surface, cools, and plunges back down. The tops of those cells are visible through good telescopes as a shifting pattern of bright granules, each one about the size of a large country, forming and dissolving over minutes. Now put the 2 ingredients together and add the sun's rotation, and you have an engine. The differential rotation takes the sun's magnetic field, which in its simplest state runs from pole to pole like lines of longitude on a globe, and winds it up. The equator flows ahead, the poles lag behind, and the threads frozen into that flow cannot stay smooth. Turn after turn, the field is stretched sideways and wrapped around the sun like thread onto a spool. But winding alone would not be enough. The rising and sinking convection cells grab those stretched field lines and twist them. And because the whole sun is rotating, those rising columns of plasma are deflected as they climb. The same sideways deflection we will meet again in the next chapter when we look at storms on Earth. The result is that the wound-up field is also continually being twisted into loops and rope like coils. And some of those coils are buoyant, and they rise. Astronomers call the whole arrangement the solar dynamo. Rotation stretches the field. Convection twists it. Together, they build and rebuild the sun's magnetism, over and over, and store enormous energy in the process. And where a coil of concentrated magnetic field finally punches up through the visible surface, it chokes the convection beneath it. Heat cannot rise as freely through that patch, so the patch runs cooler than its surroundings, and cooler plasma glows less brightly. From 93 million miles away, it looks like a dark spot. That is what a sunspot is. The blemishes Galileo tracked 400 years ago are the footprints of the sun's own tangled magnetism, and they are colossal, often larger than the entire Earth. The whole cycle of winding and tangling and breaking down builds to a crest roughly every 11 years, when spots crowd the solar face. And then the exhausted, snarled field reorganizes itself, flipped in polarity, and the winding begins again. Roughly 11 years. Not exactly. The rhythm wanders by a year or two in either direction. Some cycles run strong, and others run weak. And there was a stretch in the late 1600s, known as the Maunder minimum, when sunspots nearly vanished for decades and nobody has ever fully explained why. The sun breathes, but not like a metronome, more like a sleeper, whose slow breaths are never quite identical, and are no less trustworthy for that. You are welcome to borrow that rhythm for a while. A long breath in, a longer one out. Nothing about it needs to be exact. Sometimes the tangle does not relax gently. Twisted field lines, forced together, can snap and violently reconnect, releasing stored energy as a flash of radiation, a solar flare, and sometimes the sun hurls away a piece of itself. A billion-ton cloud of magnetized plasma called a coronal mass ejection, racing outward at millions of miles per hour. Here is where this chapter reaches your own sky. The sun's magnetism, built by that dynamo of rotation and convection, shapes a constant outflow of charged particles called the solar wind, and it powers those great eruptions besides. When gusts and storms in that wind sweep past the Earth, our planet's own magnetic field catches the blow, flexing and funneling particles down toward the poles. And where they rain into the upper atmosphere, the air itself glows, green, red, violet, in slow curtains and arcs. The northern lights, and their southern twin. Not every aurora requires an eruption. The steady wind alone, gusty and stirred, can light polar skies on an ordinary night in Alaska or northern Norway. But the grandest displays, the ones that spill far south of their usual home, ride the great storms. If you were among the many people across the United States and Europe who watched the aurora reach unusually far south in May of 2024, you have already seen this chapter happen above your own street. The sun's uneven turning, arriving as silent colored light. It can be stronger still. In September of 1859, the largest solar storm in recorded history struck the Earth, an event named for the astronomer Richard Carrington, who watched the flare that preceded it. Auroras were reportedly seen close to the tropics, and the young telegraph networks sparked and failed. In our far more wired century, a direct repeat would be a serious test of power grids and satellites, which is why agencies including NASA and NOAA now watch the sun around the clock. The sun's spin has a forecast now, and it is checked every single day. There is one more wonder here, and I saved it because it is quietly astonishing. You might reasonably ask how anyone can possibly know what the rotation is doing deep inside the sun, far below anything a telescope can see. The answer is that the sun rings. All that boiling convection is constantly striking the sun from beneath, the way 1,000 small hammers strike a bell, and the whole star vibrates with sound waves that travel through its interior and reflect back from its surface. Those waves make the visible face of the sun rise and fall by tiny amounts, and instruments can measure that motion. The sun quivers in millions of overlapping patterns at once, and by carefully separating them, physicists can work out what the waves pass through on their way. In much the same way that seismologists map the inside of the Earth using earthquakes, the field is called helioseismology, and it has traced the sun's rotation far beneath the surface. It found that the uneven, Latitude by latitude, turning continues down through the entire convective outer third of the star. And then, at a certain depth, it stops. Below that boundary, the deep interior turns much more nearly as a single body, all together, like a solid thing after all. The thin layer where those two behaviors meet is called the tachocline, and many solar physicists suspect it is where the great winding of the magnetic field is anchored. We have, in the most literal available sense, listened to the inside of a star and heard where it stops being a fluid and starts turning as one. So hold the sun in your mind one more moment. Not a steady lamp, but a slow storm of turning honey and twisting thread, boiling from below, winding itself tight and shrugging itself loose on a breath roughly 11 years long, repeated for 4.5 billion years. And every so often, it shakes a little of that stored turning free across space. And the night sky of Earth answers in curtains of light, but you do not need an aurora to watch spin painting a sky. There is a far more common signature, and it crosses the weather map on every evening news broadcast in America. For this chapter, you do not have to go anywhere at all. The spin we are about to explore is in tomorrow's forecast. In every satellite photograph of clouds you have ever glanced at without a second thought, have you ever noticed that storms around, not only hurricanes, though hurricanes are the masterpiece? Watch the weather map behind any American forecaster. The great low-pressure systems that carry rain into Chicago or snow into Denver are not shapeless blobs. They are spirals, sometimes 1,000 miles across, and they are all turning. And here is the detail that, once seen, cannot be unseen. Across the United States, across Europe, the great stormy lows of the Northern Hemisphere share a direction. They turn counterclockwise, south of the equator, in Australia, in Argentina. Their counterparts turn clockwise. The mirror image. The atmosphere did not choose this. It obeys something, and what it obeys is the turning of the ground beneath it. Let me show you how. Because this is one of those explanations that feels like a magic trick right up until the moment it feels obvious. Start with something you already own from our first chapter. The Earth's surface moves fastest at the equator, where it must cover the planet's full waistline in a single day. Toward the poles, the circles shrink, and the ground moves more slowly. Someone in Miami is being carried eastward noticeably faster than someone in Minneapolis, simply because Miami rides a wider circle. Now a thought experiment. Imagine a mass of air near Miami beginning to drift north. That air carries its fast eastward motion with it, but as it travels, the ground beneath it is moving eastward more and more slowly. The air is now outrunning the land it crosses. So to anyone standing on that land, the air appears to curve ahead of itself, bending east, to the right of its path. The trick works in reverse too. Air flowing south from Minneapolis arrives carrying less eastward speed than the ground beneath it. So it falls behind, and again, to an observer on the ground, it appears to curve to the right. That is the entire secret. In the northern hemisphere, things moving freely across large distances appear to bend rightward. In the southern hemisphere, everything mirrors, and paths bend left. Nothing is pushing the air sideways. The air moves as it moves, and the ground turns underneath it at different speeds in different places. The curve is real to us because we live on the turning ground. The effect carries the name of the French scientist Gaspard Gustave de Coriolis, who worked out the mathematics of motion in rotating systems in the 1830s. Now watch it assemble a storm. A patch of low pressure forms, often over warm ocean water. A region where air is rising and the pressure at the surface drops. Air begins flowing inward from every direction to fill the low. The way air rushes into any gap. If the Earth stood still, that would be the whole story. Air slides straight in from all sides, fills the low. Done. But every inflowing stream is bent rightward as it travels. Air arriving from the south bends and misses the center, sliding around one side. Air from the north bends and slides around the other. Every stream misses. Every stream slides around, and together they braid themselves into a rotation, counterclockwise, wrapping tighter and tighter around the low like water, circling a drain that nothing is permitted to reach. Add the engine of warm ocean water, feeding heat and moisture into the rising core, and the pinwheel can grow into the largest storm structure this planet produces. Seen from orbit, a mature hurricane is a portrait of everything tonight has been about. An eye of calm, wrapped in a spiral of inherited motion, hundreds of miles wide, turning because the Earth turns. One honest refinement. So the picture in your head matches the real sky. This rightward bending organizes the large and the slow, rising air in a deep, low spirals, counterclockwise in the north, but sinking air in a fair weather, high spirals the opposite way, clockwise, which is why those two kinds of system, on a weather map, turn against each other like meshing gears. Very near the equator, the effect grows too faint to organize anything, which is why hurricanes are never born there. And small, brief swirls follow their own local rules entirely. The Earth's turning is a choreographer of continents and weeks. It does not manage every dancer, which brings me to a correction I owe you. You may have heard that water drains from sinks counterclockwise in America and clockwise in Australia. It is a charming idea. It appears in films and travel stories. And it is simply a myth. The Coriolis effect is real but gentle, and it needs size and time to matter. Hundreds of miles and many hours. A bathroom sink is a few inches across and drains in seconds. At that scale, the Earth's turning is overwhelmed a millionfold by ordinary things. The shape of the basin, the angle of the tap, the swirl left over from filling it. Researchers have coaxed a tiny Coriolis preference out of heroically careful laboratory basins. Perfectly symmetrical, left to settle for many hours first. In your bathroom, never. Your sink obeys your plumbing. The sky obeys the planet. There is real satisfaction in knowing a piece of physics precisely enough to know exactly where it applies and where it does not. Rest inside the eye of that idea for a moment. The one still place in any turning system. Before we push outward one last time in this chapter, because a lovely question follows. If our modest spin combs our storms into spirals, what does weather look like on a world that turns much faster and is made of almost nothing but atmosphere? Jupiter is 11 times the width of the Earth, and yet its day is the shortest of any planet. Just under 10 hours. A world that could swallow 1,000 Earths, completing a full rotation before your workday ends. Its equator races along at tens of thousands of miles per hour, and it has no continents, no oceans, no surface anywhere to slow its winds with friction, spin that fast, on a body that large, and the bending of paths is no longer a gentle suggestion. Weather on Jupiter cannot wander north and south in great looping journeys the way ours does. It is combed, relentlessly, into bands, running parallel to the equator, and that is exactly what any decent telescope shows. Stripes, cream and rust and brown, jet streams stacked from pole to pole, flowing in alternating directions at hundreds of miles per hour. And between them, storms, thousands of spinning storms, ovals and eddies purled along the boundaries where the bands rub against each other. One of those storms deserves a moment of quiet. In Jupiter's southern hemisphere sits an oval the color of brick, wide enough to swallow our whole planet, though not by as much as it once could. It is called the Great Red Spot, and it has been shrinking for as long as careful measurements have existed. A century ago, it was perhaps twice the Earth's width. Today, it is closer to a little over one. It is a single storm, spinning counterclockwise with winds of hundreds of miles per hour. And astronomers have watched it continuously since at least the 1800s. Observers in the 1600s recorded a great spot that may or may not have been the same one. Even by the cautious count, this single storm has outlasted every nation on your passport. Hurricanes on Earth die within days, starved the moment they leave warm water, shredded by friction with land. Jupiter's storm has no land to strike, and it lives inside a deep, planet-wide flow that can feed it rather than tear it apart. Sustained by the giant's own internal heat and by swallowing smaller storms whole. Whether it will survive another century is genuinely uncertain, but it has already outlived every astronomer who ever mapped it. Hold that image as we leave. A storm older than nations, slowly shrinking, still turning. Because the universe builds storms out of stranger materials still, and it spins some objects so fast that the very idea of a day breaks apart into something almost beyond belief. Scattered through our galaxy are the collapsed hearts of dead stars, heavier than the sun, crushed down to the size of a city, and some of them turn hundreds of times every second. The story of how we found them begins with a graduate student, a field full of wire, and a signal so strange that for a few weeks it was labelled, half seriously, with the initials of Little Green Men. Cambridge, England, the autumn of 1967. In a field outside the city stands one of the strangest telescopes ever built. It has no dish, no dome, no eyepiece. It is 4 acres of wooden poles and wire, more than 1,000 posts strung with over 100 miles of cable, looking less like an instrument of science than like a vineyard planted by someone who forgot the grapes. It is a radio telescope built to catch the faint radio whispers of distant galaxies, and much of it was hammered together by hand, by students, over 2 years. One of those students is a young woman named Jocelyn Bell, 24 years old, from Northern Ireland, working on her doctorate. Her job, now that the array is finally listening, is to analyze its output. And the output is not a picture on a screen. It is ink on paper. The telescope signals drive pens that scrawl wavering lines onto rolls of chart paper, about 100 feet of paper every day. And Bell's task is to read it, all of it, by eye, mile after mile of wiggles, learning to distinguish the signature of a distant galaxy from the crackle of human interference. A passing car, a badly wired refrigerator, the general electrical noise of a civilization, and in October of that year, working through her endless scrolls, she notices something she cannot classify, a little stretch of scruff, as she later called it, a patch of ragged signal less than a quarter-inch wide on the paper, buried among the miles. It does not look like a galaxy. It does not look like interference either. And here is the detail that changes everything. The detail that makes this one of my favorite stories in all of science. She remembers having seen it before, out of 100 feet of paper every day. She recognizes a quarter-inch of scruff as a repeat visitor. She goes back and checks. It has appeared before, from the same patch of sky, keeping time with the stars rather than with the clock. Anything that rises and sets with the stars is not a refrigerator. It is out there. So Bell and her supervisor, Anthony Hewish, set up a faster recorder to stretch that scruff out and see its shape. For weeks the source teases them, fading, hiding, giving nothing. Then, in late November, the fast recorder catches it in full voice, and the ink draws something no astronomer has ever seen. Pulses. Sharp, clean, evenly spaced pulses of radio energy, arriving about every 1 1/3 seconds, not roughly, precisely, pulse after pulse after pulse, spaced with the regularity of a fine clock, arriving out of the dark between the stars. Astronomy has no explanation for this. Nothing known blinks like that. Stars do not tick, and so, sitting with data too strange to publish and too solid to dismiss, the team gives the source a nickname, half in jest and half not, because a signal that precise, arriving from one fixed point in the sky, is exactly what an artificial beacon might sound like. They label it LGM1, Little Green Men. You can smile at that in the dark, because within weeks the joke dissolves in the best possible way. Bell, back at her scrolls, finds a second stretch of scruff in a completely different part of the sky, and the fuzz-wheatst recorder catches it too, ticking at its own rate. Then a third, then a fourth, and that settles it. Gently and firmly. One beacon might be little green men, 4 beacons, scattered across the galaxy, all of them signaling plain vanilla Earth. Strains belief past breaking. Whatever these objects were, they were natural. The universe itself contained clocks. The discovery was announced in 1968, and a journalist soon coined the name that stuck: pulsating stars. Pulsars. Now comes the question all of astronomy asked that year, and it is the question that places this chapter at the heart of our night. What in nature can tick like that? What object can produce a flash every 1 1/3 seconds? With that kind of precision, over and over. Think it through with me, slowly, using nothing but what tonight has already given you. For an object to blink that fast, some part of it must be moving that fast, most plausibly turning that fast. So ask what can turn completely around in about a second and survive. Not the sun, spun once per second. The sun would fly apart instantly, shredded by its own rotation, because its gravity could never hold material moving at such speed. To turn that fast and live, an object must be almost unimaginably compact, its mass crushed so close to the axis, its surface gravity so ferocious, that even that whirling cannot tear it loose. Astronomers ran the numbers, and only one candidate survived. An object that had been proposed on paper back in the 1930s, but that many had quietly doubted, was real. A neutron star. Here is what a neutron star is. Built the way tonight has taught us to build everything, with the skater and the fall. When a star, much more massive than the Sun, exhausts its fuel, its core loses the outward pressure that spent millions of years holding gravity at bay. And in less time than it takes you to exhale, the core collapses. A ball of matter larger than Earth crushes down into a sphere perhaps a dozen miles across, the size of a city, while the star's outer layers detonate as a supernova. The same kind of blast that may once have seeded our own quiet cloud. What remains is matter compressed past every familiar limit. Protons and electrons crushed together into neutrons, packed so tightly that a single teaspoon of the material would weigh about 1 billion tons. More than a mountain, a sun and a half of mass. In the footprint of a small town, and now the skater takes over. At the very edge of what physics allows, that collapsing core was turning before it fell. Slowly, perhaps once a month, the way the sun turns, but it has just pulled its arms in by a factor of tens of thousands, from hundreds of thousands of miles across down to a dozen. The books must balance. The mass has gathered impossibly close to the axis, so the rate of turning must soar. And it soars beyond anything else in the universe made of matter. The newborn neutron star turns not once a month, but many times every second. Its magnetic field, concentrated by the same collapse, becomes trillions of times stronger than Earth's, and it channels beams of radiation out of the star's magnetic poles. 2 searchlights, fixed to a spinning lighthouse, and if the geometry happens to sweep one of those beams across the Earth, then once per rotation, our telescopes catch a flash, a pulse, a tick. That is what Jocelyn Bell found in her scruff. Not a beacon built by intelligence, but something in its own way more astonishing. The crushed, spinning heart of a dead star, sweeping its light across her field of wires with the regularity of a clock. A ball of neutrons has no atmosphere around it, no ocean, no surface friction to lean on it, and so it simply keeps turning, and keeps turning, faithful to the skater's law, across immense spans of time, not quite forever. Though, even a lighthouse pays a toll. Those beams and that whirling magnetism carry energy away into space, and so every pulsar slows, imperceptibly, its ticking stretching by tiny fractions across the centuries. The clocks of the universe do run down. They simply do it more gracefully than anything else we know of. And the universe was not finished showing off. In the decades since, astronomers have found pulsars that make that first one look sleepy. Some ancient pulsars, spun back up by pulling material off a companion star, rotate hundreds of times every second. The fastest one known turns more than 700 times each second. Try to hold that. If it will hold, a sphere heavier than the sun, the size of a city, completing 700 full rotations in the time it takes you to say 1001. Its equator moving at a substantial fraction of the speed of light. It is the skater's principle written at the absolute limit of what matter can endure. And it is real. And it is ticking in our sky at this moment. One more grace note before we drift on, because it deserves its place. The precision of these clocks turned out to be a gift. Pulsar timing is now so exact that astronomers use networks of them as a galaxy-sized instrument, watching for the faint stretching of space itself between us and them. And the very first planets ever confirmed around another star, in 1992, were found orbiting a pulsar, betrayed by tiny hiccups in the arrival time of its ticks. Bell's quarter-inch of scruff grew into an entire science. It is worth adding that the 1974 Nobel Prize for the discovery went to Hewish and a colleague, and not to Bell, a decision that has been debated ever since, and one that Bell herself has discussed over the years with a generosity that is its own kind of lesson. In 2018, she received a major International Physics Prize for her life's work, and she donated the entire multi-million-dollar award to help students from underrepresented backgrounds to become physicists. The person who found the universe's clocks spent her own time winding up the next generation. Let the ticking fade now, the way a clock in a quiet house fades once you stop listening for it. Matter, at its absolute limit, can spin 700 times a second and hold itself together, but some collapsing stars are too massive even for neutrons to stop the fall. For them there is no final flaw. The fall simply wins. And carry this question through that door. Drowsy and strange. The skater's law says spin cannot be destroyed, only passed along. So when a spinning star collapses past the point of no return, past the point where it has any surface left at all, where does the spin go? Everything we have met tonight, however strange, has had a surface. The skater has her skates. Venus has its scorched plains. Even the neutron star, crushed past all imagining, still has a crust. A real place, a dozen miles across, where the spinning object ends and space begins. You could, in principle, point at the thing that is turning. A black hole takes even that away. And yet, a black hole spins. This is the deepest water of our whole journey. So let me promise you something before we wade in. Nothing here requires effort. Strange is not the same as difficult. And we will move the way you would walk into a dark, calm lake at night. Slowly, and only as far as feels good. Begin with the fall. A star far more massive than the sun runs out of fuel, and its core collapses. Exactly as we watched in the last chapter. If the core is modest, the collapse slams to a halt at the neutron star, matter's final flaw. But if the core is heavy enough, somewhere past roughly 3 times the mass of the sun, then not even neutrons pressed shoulder to shoulder can hold the weight. The floor gives way, and as far as the physics we currently possess can follow, nothing stops the fall again. The equations of Einstein's general relativity, taken at face value, say the material collapses without limit, toward a center where the mathematics itself breaks down and stops giving sensible answers. What truly happens in that innermost place? Nobody knows. It sits at one of the great frontiers where our best theories openly admit they are unfinished, waiting for some deeper description that unites gravity with the physics of the very small. What we do understand, with real confidence, is the outside. Around the collapsed star, there remains a boundary in space, a spherical surface of no return that astronomers call the event horizon. It is not a wall. It is not made of anything. It is simply the distance at which gravity has grown so strong that escaping would require moving faster than light. and nothing moves faster than light. Whatever crosses that boundary does not come back out. From the outside, the star has gone silent and dark. Its gravity remains, like a voice still filling an empty room. The black hole is still very much a part of our universe. It still pulls on everything nearby. It has simply closed its door, but it kept something. Let your breathing slow, the way the surface of that lake goes still. Because this is the turn the whole chapter rests on. The star was spinning when it fell, and the skater's law does not care that the star's surface is gone. Spin cannot be destroyed, only passed along. And this spin was not passed to anything. It fell inward with everything else. So the black hole holds it. In the mathematics of relativity, worked out in full for spinning black holes by the New Zealand mathematician Roy Kerr in 1963, a black hole is described almost entirely by just two numbers: its mass and its spin. Nearly everything else about the star that fell, its couleur, its chemistry, the long story of its life, lies beyond our reach, behind that horizon. Mass and spin remain, written into the shape of space itself. And what does spin even mean? For an object with no surface, here the universe becomes stranger, and I think more beautiful, than anywhere else tonight. Einstein's great insight was that gravity is not a force reaching across space. Gravity is the shape of space. Mass bends the space and time around it, the way a heavy sleeper bends a soft mattress, and everything nearby moves along those curves. That much you may have heard before, but the theory predicts something further, quieter, and much wilder. A spinning mass does not merely bend space, it drags it. The rotation grips the fabric of space and time surrounding it and pulls it slowly around. The way a spinning spoon in a jar of honey does not just sit in the honey, but sets the honey itself turning. Physicists call this frame dragging, and it means something wonderful. Around a spinning object, empty space is not still. The nothingness itself circulates. Around a rapidly spinning black hole, that dragging becomes overwhelming. Just outside the horizon, there is a region called the ergosphere, and within it, nothing can hold still. Not a spacecraft with any engine ever designed. Not light itself. You could fire every rocket ever built against the current, and you would still be carried around, because you would not be moving through space so much as space itself would be moving, and you are inside it. The way a leaf in a whirlpool is not disobeying the river. Inside that region, the universe has a direction, and the direction is around. The spin of the vanished star has become weather in the fabric of reality, a claim that large deserves the question this journey always asks. How could anyone know? It is one thing for mathematics to predict dragged space, and quite another to catch the universe doing it. So let me tell you about one of the most patient experiments ever performed. It was called Gravity Probe B, a NASA mission decades in the making. Launched in 2004. The idea was simple to state and brutally hard to do. Put the most perfect gyroscopes ever manufactured into orbit around the Earth. Align them with a distant star. And watch. A gyroscope holds its direction faithfully, exactly the way Foucault's pendulum held its swing. If the space around our spinning Earth were perfectly still, those gyroscopes would keep pointing at that star forever. But if Einstein was right, the Earth's own rotation should drag the space around the satellite. very slightly, and the gyroscopes, floating inside that gently turning space, should drift. The predicted drift from frame dragging was minuscule, an angle comparable to the width of a human hair seen from several miles away. To measure it, the team built quartz spheres described as among the most perfect ever made by human hands, spinning in vacuum, chilled to near absolute zero, shielded from nearly every disturbance the universe could offer. And the gyroscopes drifted. After years of flight and years more of painstaking analysis, results announced in 2011 confirmed it. The axes had been pulled, by the predicted whisper, in the predicted direction. The Earth, our own ordinary 24-hour Earth, measurably drags the space around it as it turns. Be careful with what that means. And generous, too. What was measured directly is the weak version of the effect. In the mild gravity around a small planet, nobody has flown a gyroscope around a black hole. But the same theory that passed this test has passed a long series of others. And it predicts that near a rapidly spinning black hole, this same effect grows monstrous, from a hair's width of drift into the whirlpool and the ergosphere. And the observations we can make from a distance agree. Astronomers read the light of superheated matter spiraling into black holes, vast whirlpools of gas glowing in X-rays as they drain inward. And the patterns in that light match what is expected around spinning holes. Some appear to be turning at close to the fastest rate relativity permits. In 2015, the LIGO observatories detected ripples in space itself. For the first time, gravitational waves from two black holes merging more than 1 billion light-years away, arriving as a faint chirp in instruments on Earth. Woven into the shape of those waves is information about how fast the two holes were turning. We are, in the most literal sense, beginning to hear how black holes spin. Take one long breath and let this chapter fold itself small enough to sleep on. The rule we learned from a figure skater has survived every extreme the universe could throw at it. It survived the death of stars. It survived the disappearance of every surface that could be said to be spinning. When there was no longer any object left to do the turning, the universe did not cancel the turning. It wove the turning into space itself. That is how seriously reality takes this one law. It would sooner set the void circulating than let the books go unbalanced. We have followed spin about as deep as it goes. So now let us come up for air and go wide instead. Wider than we have gone all night, until every star you have ever seen becomes a single grain of light among hundreds of billions. And all of them together turn out to be doing the same thing everything else tonight has done. On a truly dark night, far from city lights, in the mountains of Montana or on the high plains of Spain, you can look up and see a pale band of light arching across the entire sky, soft as breath on glass. People have watched it forever. The Romans called it the Road of Milk. Nearly every culture on Earth gave it a name. A river, a path, a seam in the tent of the sky. It is the Milky Way. And here is what you are actually seeing when you see it. You are inside a disk of stars, looking along the disk from within. That glowing band is the combined light of millions upon millions of distant suns, too faint and too crowded for your eye to separate. The way the individual trees of a far forest blur into a single haze of green, our galaxy is a spiral, a flattened wheel of stars, gas, and dust. Somewhere around 100,000 light-years across, holding by most estimates between 100 billion and 400 billion stars. Numbers that size slide off the mind. So try this one instead. If the entire solar system, everything we have visited tonight, out past the farthest planet, were shrunk down to the size of a coin resting on your nightstand, the Milky Way, at that same scale, would stretch about halfway across the continental United States. A coin, and a distance like New York to Denver. That is our address, and the whole thing is turning. The Milky Way rotates. Every one of those hundreds of billions of stars is in orbit around the galaxy's center. Our sun rides that wheel a little more than halfway out from the middle, in a quiet neighborhood between spiral arms, carrying the Earth and you along at roughly 500,000 miles per hour. And yet, even at that speed, one single lap takes about 230 million years. Astronomers call that span a galactic year, and I want to spend a slow moment inside it, because it may be the most humbling clock there is. 1 galactic year ago tonight, the Earth existed, and was already ancient. But you would not recognize the place. The continents were gathered together into a single enormous landmass. There was no Atlantic Ocean. The interior of that supercontinent was vast desert, hundreds of miles from any coast in every direction, and the very first dinosaurs. Small, quick, unremarkable creatures that nothing about would have suggested a future, were just beginning to appear. Since that night, the Earth has completed one single orbit of its galaxy. In that one lap, the continents unmoored and drifted apart into the shapes on your classroom maps. The Atlantic opened. The dinosaurs rose, spread into every corner of the world, ruled for well over 100 million years, and ended in a single terrible afternoon. Flowers appeared, and the insects that visit them. Grass appeared, and grass is far younger than most people guess. Mammals crept out from the undergrowth. Whales walked into the sea. Mountains rose and wore down to hills. Ice sheets came and went again. And, somewhere in the last thin sliver of that lap, so recent it barely registers, some upright animals on an East African plain began carrying stones, and then carrying stories. And eventually, one of them looked up at that pale band of light and gave it a name. All of that, everything in every book you have ever read about the deep past, fits inside a single turn of the wheel you are riding right now. Our sun, middle-aged, has made the trip perhaps 20 times. Now, where did all that turning come from? You might expect me to tell the cloud story again. One vast whisper, one collapse, one flattening. Our little solar system, written 10 billion times larger, and there is real truth in that shape. Gas that cools and settles does tend to flatten into a disk, for the same reasons ours did, and a galaxy is genuinely a spinning, flattened structure. But a galaxy is not simply a solar system enlarged, and the difference is worth knowing, because it is lovelier than the simple version. A galaxy does not get its turning from one private whisper in one isolated cloud. It grows up in a crowd. Galaxies form inside a vast web of matter that stretches across the universe, fed by streams of gas flowing inward along the strands of that web. In their youth, they are tugged and torqued by the gravity of their neighbors, each pull imparting a little twist, and they are assembled. across billions of years. From mergers, smaller galaxies falling in and blending, each arrival bringing its own motion into the mix. A galaxy's spin, then, is not a single inheritance. It is a running total, less like one skater, and more like a whole rink full of them, joining hands over billions of years. The final rotation, a long negotiation among everything that ever fell in. Our Milky Way is still negotiating. It is pulling in small neighboring galaxies, even now, and their motion is being folded slowly into the whole. The skater's law governs every step of it. Spin is still conserved, still traded, still amplified when things collapse. It is only that a galaxy's books record billions of transactions instead of one. Let the wheel itself set your pace here. It is the slowest carousel in existence, and you have ridden it your entire life without once feeling it move. One more wonder before we follow this chapter's thread to its famous loose end. The galaxy does not turn like a solid wheel, whose rim and hub come around together. It is a swarm, and every star follows its own orbit at its own pace. Inner lanes lapping outer lanes, endlessly, which raises a puzzle you may already feel forming. If the galaxy has been shearing like that for 10 billion years, why have the spiral arms not long since wound themselves up into a featureless smear, wrapped around the center hundreds of times and smoothed away? Yet there they are, in every photograph of every spiral galaxy. Those grand, loose, elegant arms. One influential answer, developed since the 1960s, is that the arms are not objects at all. They are patterns, traffic jams, zones of crowding that stars and gas drift into, pass through, and eventually leave. The way cars pile into a slow stretch of highway and escape out the front while new cars feed in from behind. The jam persists while the cars keep changing, and where gas crowds together, it collapses and ignites, which is why the arms glow so brightly, lined with brilliant, short-lived young stars like construction lights along the slowdown. It is a beautiful picture, and in many galaxies it seems to capture something real. Astronomers will also tell you that spiral arms come in more than one kind, and that some may be shorter-lived ripples, raised and raised again across the ages, stirred up by companions passing near. The arms keep some of their secrets. The turning underneath them does not, or so it seemed, because in the 20th century, astronomers finally did the careful bookkeeping on that turning. They measured how fast galaxies actually rotate, ours and many others, and compared it against how fast the visible stars and gas said they ought to rotate, and the numbers refused to agree. Not by a little. The outer stars were moving far too fast. Turning at those speeds, the galaxies we see should be flinging themselves apart. They are not. Something is holding them together, something no telescope has ever seen. Vera Rubin fell in love with the sky as a child. Watching the stars wheel past her bedroom window in Washington, D.C. in the 1930s, she traced their paths in her mind, night after night, and memorized the meteor trails so she could write them down in the morning. Her father, an engineer, helped her build her first telescope out of a cardboard tube and a lens ordered through the mail. It barely worked. It did not matter. She was already claimed by the turning sky, the way some people simply are. She wanted to study astronomy at a time when much of American science was not built to welcome her. In the late 1940s, she inquired about Princeton's graduate astronomy program and was told that women were not admitted. Princeton would not admit a woman to that program until 1975. So she went elsewhere, studied at Cornell and then Georgetown, raised 4 children, and kept working steadily at the edges of a field that kept suggesting she might belong somewhere else. One story from those years is told by colleagues who observed alongside her. Granted precious nights at the Great Palomar Observatory in California, she found that the mountain had no restroom for women. So she cut a paper skirt, taped it over the figure on a door, and announced that the problem was now solved. Whether every detail is exactly right, the story has been told by people who were there, and it captures her method precisely. She did not storm gates. She quietly declined to accept that they were closed. And then she got back to work. And the work she chose, by the 1960s, was deliberately quiet. Rubin had brushed against the famous, competitive corners of astronomy and disliked the elbowing. So she went looking for a problem she believed was so unglamorous that nobody would fight her for it. She decided to measure, carefully, how galaxies rotate. You can smile at that in the dark. The safest problem in astronomy, the one that came apart in her hands. Here is what she did. And by now, you have every tool needed to follow it. Working with a colleague at the Carnegie Institution named W. Kent Ford, who had built an exceptionally sensitive instrument for splitting starlight into its spectrum, Rubin pointed telescopes at nearby spiral galaxies, beginning with our great neighbor, Andromeda. Light from a rotating galaxy carries its motion written inside it. Light from the side of the disk turning toward us is compressed, shifted slightly toward blue. Light from the side turning away is stretched, shifted toward red. It is the same effect that bends the pitch of a passing siren, only written in color instead of sound. Read those shifts, point by point, from the bright center of a galaxy out to its faintest edge, and you have drawn what astronomers call a rotation curve, a simple graph of how fast the galaxy turns at every distance from its middle, and everyone knew what that graph should look like. This is the crucial part. So let it arrive slowly. Our own solar system taught the rule centuries ago. Nearly all of the solar system's mass sits at the center, in the sun, and so the planets obey a clean, falling pattern. Mercury, close to the mass, races around in 88 days. Neptune, far out beyond almost everything, drifts along several times more slowly. Speed falls as distance grows, because gravity thins with distance. A galaxy's light says its mass is arranged much the same way, blazing dense at the core and fading toward the edges. So the stars far out in the rim, orbiting beyond most of the glowing material, should be the Neptunes of the galaxy. The rotation curve should rise near the center, then bend over and fall, gracefully, all the way out. Every textbook expected it. Rubin and Ford measured Andromeda, point by patient point. Through the late 1960s, the inner curve rose, exactly as expected. Then it reached the region where it was supposed to bend over and fall. It did not fall. The curve went flat. Stars halfway out were orbiting fast, and stars far beyond them, out, where the galaxy's light dims toward nothing, were orbiting just as fast. They measured further, into the faint fringes, expecting at every step to catch the decline. flat. They moved on to other galaxies. Dozens of them eventually. Spirals of every size and brightness. And the same stubborn shape emerged from every one, rising, then flat, out to the last measurable star. Radio astronomers, tracing cold hydrogen gas far beyond the visible stars, found the flatness continuing even out there, where there was almost nothing left to see at all. Now, stop and feel what that graph is saying, because this is the moment the invisible walked into the room. Stars at the rim, moving that fast, around only the mass we can actually see, cannot stay. It is not a small discrepancy. At those speeds, the visible galaxy's gravity is nowhere near enough to hold them. They should let go, fly outward, and scatter into the dark. And a couple of galactic years of that would unravel the entire disk. Yet there Andromeda stands, 10 billion years old, Cerny, whole, visibly not exploding. The stars are held by the gravity of something, and when the bookkeeping was done, the something was enormous. To hold each galaxy together, there had to be additional matter, unseen, shining at no wavelength anyone could detect, arranged not in the bright disk, but in a vast, roughly spherical halo, swallowing the visible galaxy the way a large clear snow globe swallows the small figure at its center. And there had to be a great deal of it. Across the universe, the current accounting runs to roughly 5 parts unseen matter for every 1 part of the ordinary kind, which is to say, most of the matter in the cosmos appears to be something that has never once glowed. Astronomers call it dark matter, and the name is really a confession, because dark here does not mean black, it means unknown. Half a century later, after deep underground detectors waiting patiently for a dark matter particle to brush against ordinary atoms, after particle colliders hoping to forge one, after telescopes mapping its gravity across the sky, nobody has identified what it is. Its gravitational presence is written everywhere. It bends light around distant galaxy clusters. It shaped the pattern of the early universe's leftover glow. It sculpted the very web along which galaxies grew. The case from gravity is overwhelming, and all of it agrees. The substance itself has never been caught. A minority of researchers ask instead whether the laws of gravity themselves might need adjustment at galactic scales. And although the consensus stands firmly with unseen matter, the fact that the question can still be asked tells you how much genuinely remains open. Fairness also asks me to widen this story beyond a single hero, because science is a relay, and Rubin would be the first to say so. Hints of missing mass were far older than her work. In the 1930s, the astronomer Fritz Zwicky weighed an entire cluster of galaxies by the motions of its members and found them moving far too quickly for the visible mass to explain. Around the same time, Horace Babcock measured Andromeda's outer regions and found them turning suspiciously fast. For decades, those clues sat at the margins of the field, easy to set aside as measurement trouble or special cases. What Rubin and Ford did was make the anomaly undeniable. Clean, repeated, systematic measurements. Galaxy after galaxy after galaxy. The same flat curves every time, until the community had nowhere left to look away. She was not the first to glimpse the invisible. She was the one whose patient bookkeeping made the invisible impossible to ignore. In science, that is very often the harder job. Rest inside the picture she left us. Every galaxy you have ever seen photographed. All that light, all those stars, is only the small bright center of something several times larger that nobody has ever seen. The luminous universe is the figurine. The snow globe is dark, and hold the method close. Because it is the quiet lesson of her chapter. All night. Spin has been a memory. But spin is also a scale. It weighs things. A rotation curve is a galaxy placed on a balance. And when the balance read several times heavier than the light could account for, the spin was telling the truth, and the light was not. Rubin, asked late in life how it felt to have spent her career uncovering a universe that turned out to be mostly invisible, gave answers of remarkable calm. Not knowing, she suggested, simply meant there was more to find. She died in 2016, still curious. And in 2025, a great new observatory in Chile, built to survey the entire southern sky and to map dark matter's gravity in unprecedented detail, began its work carrying her name, the Vera C. Rubin Observatory. The child at the window ended up with a mountaintop watching the sky for her. Her discovery hands us the last big question of the night, the one everything has been climbing toward. We have now seen spin at every scale there is. Skaters, planets, dead stars, black holes, galaxies, even the invisible halos that cradle them. Everything, at every level, turning. So does it go all the way up? Is the universe itself, the whole of it, spinning? Every question tonight has had the same shape. We found a thing. We watched it turn. And we traced the turning back to something larger that handed it over. Moons around planets. Planets around stars. Stars around galaxies. Galaxies gathered by gravity into clusters. Drifting and swinging around one another in ensembles so slow that billions of years pass before they trade places. At every rung of that ladder, rotation, and now we stand on the top rung, and there is only one question left to ask. The universe itself, the totality, does it spin? The first thing to say is that this is a real scientific question, asked seriously by serious people, and it is much stranger than it sounds. Notice what spinning has meant all night. The skater spins relative to the rink. The Earth spins relative to the distant stars, which is precisely what Foucault's pendulum revealed under that dome in Paris. Every spin we have measured has been measured against something outside itself. But the universe has no outside. There is no rink. There are no farther stars beyond it to check against. If the whole of everything were rotating, what could it possibly be rotating relative to? Here is the surprisingly deep answer, and it is gentle enough to hold half asleep. It could rotate relative to itself, and physics would know. Remember, gravity probe B. A gyroscope does not need to look out a window to sense rotation. Spin leaves internal fingerprints. And in a rotating universe, the mathematics of relativity says those fingerprints would be woven into the sky itself. The great logician Kurt Gödel, Einstein's friend and walking companion at Princeton, proved this point in 1949 by finding an exact solution to Einstein's equations describing an entire rotating universe. Gödel's universe is lawful and mathematically consistent, and it is famously strange, because in it, rotation twists space and time so thoroughly that paths looping back into the past become possible in principle. Einstein is said to have found it unsettling. The point of the exercise was never that our universe is like that. The point was that the question is legitimate. The equations permit rotating universes. So, whether ours rotates is not philosophy. It is measurement, and we have something magnificent to measure with. The universe began, by all current evidence, about 13.8 billion years ago, in a hot and dense state that has been expanding and cooling ever since. For its first few 100,000 years, all of space glowed, filled with light scattering endlessly through hot plasma. Then the cosmos cooled enough for atoms to form. Space turned transparent, and that first light was set free. It is still traveling, stretched by the expansion of space into faint microwaves. It arrives from every direction, all the time, a wall of ancient light standing behind everything else in the sky. Astronomers call it the cosmic microwave background, and, since its discovery in 1965, spacecraft named COBE and WMAP and Planck have mapped it across the entire sky in exquisite detail. It is, in the most literal sense available to us, a baby picture of the universe. Now the key, a rotating universe, could not keep that baby picture symmetrical. Rotation defines an axis, a preferred direction, and across billions of years it would stamp a particular lopsided signature onto that ancient light. A subtle patterning arranged around the axis. The signature is calculable in advance, which means it can be hunted for. So researchers hunted. They combed the full sky maps for any credible sign that the cosmos prefers a direction. One widely cited analysis of the Planck data, published in 2016, put the outcome about as cleanly as science can. No convincing evidence of rotation, and limits so tight that any overall turning would have to be almost inconceivably slow, far too slow to have meaningfully shaped anything the universe has ever done. As far as the oldest light can testify, the cosmos as a whole shows no preferred axis. It does not appear to spin. Be careful, though, with how far that lovely result reaches, because here the honest path is narrow, and the narrowness is worth seeing clearly. What the measurements establish is exactly what I just said, and no more. On the largest observable scales, there is no credible sign of a shared, coherent rotation, no axis around which the whole sky turns. What the measurements do not establish is any grand cosmic ledger in which every spinning galaxy is neatly matched against an opposite spinning galaxy somewhere else. That is a different claim entirely, and nothing in this data delivers it. Whether one can even meaningfully define the total spin of an entire universe is a subtle question inside Einstein's theory, one that mathematicians still handle with considerable care. So the honest summary is narrower than poetry would like, and stronger than poetry needs. The universe is full of turning things. The universe as a whole shows no sign of turning. Both of those stand on solid ground, and the gap between them is simply a place where our knowledge, for now, respectfully ends. There is something restful in a frontier that behaves like that. From time to time, researchers do report hints of large-scale oddities in the sky, faint alignments, curious asymmetries, and each claim gets weighed and tested, and, so far, none has held up as evidence that the cosmos turns. The checking continues with better instruments, which is exactly as it should be. The question is being asked properly. with telescopes, rather than with confidence. So let the top rung of the ladder rest unfinished. In the most peaceful possible way, every rung below it turns. The ladder itself, as far as we can see, does not, which leaves one last stone, and you may already feel it under your hand. All night I have said, again and again, that spin cannot be destroyed, only passed along, traded, handed off. If that is truly the law, then every single turn we have met tonight raises a shadow question we have never once stopped to ask. When the skater speeds up, when the cloud collapses, when the Earth spins the moon slowly outward, something, somewhere, must be receiving the other side of that trade. So before sleep, one last short journey. Let us go looking for the missing half of every spin we have met tonight. All night we have been collectors. Planets, storms, dead stars, galaxies, each one turning, each one carrying its inherited whisper, and a good collector, at the end of a long night, checks the accounts, because the law we have leaned on since the ice rink has a stricter meaning than we have yet let it show. It does not only say that spin persists. Within any system, we can treat as closed off from the rest, left to itself. The total amount of turning stays exactly what it was, which means that when something in that system starts turning one way, the change has to be paid for somewhere else inside it. Nature does not simply write a single entry and move on. So where are the payments? Where is the other side of everything we met tonight? Start with something you could hold in your hands tomorrow. There is a classic demonstration that physics teachers have used for 100 years. And if you have ever seen it, you will remember it. A person sits on a swiveling stool, holding a bicycle wheel by its axle. Someone spins the wheel. Nothing much happens. Then the seated person tips the spinning wheel over onto its side, and the stool begins to turn, carrying them slowly around. They did not push against anything. Nobody touched them. They simply changed the direction the wheel's spin was pointing. And the stool answered by turning the other way, taking up exactly the amount required to keep the total unchanged. Let the wheel back upright, and the stool stops. The books balance in real time, in a school hallway, in front of a class of teenagers who almost always laugh. That is the law in miniature. And now, watch the counterweights of the night reveal themselves. One at a time. The moon, remember, is drifting away from us, 1.5 inches a year. That is a trade. And now you can see both sides of it. The Earth's spin is the account being drawn down. The moon's widening orbit is the account being filled. Day length converted into distance. Through the patient bookkeeping of the tides, with nothing lost in between. Notice something in that example, though, because it matters for everything that follows. The moon's share did not arrive as spin. It arrived as orbit. The balancing does not have to come back as another spinning object. It can be paid in a wider orbit, or in escaping material, or carried off by radiation, or spread so thinly across so many things that no single recipient can be pointed to at all. What must balance is the total. Nature is not obliged to hand you a tidy partner for every turning thing. The skater is a subtler case, and a lovely one. When she pulls her arms in and blurs, where is her counterweight? The answer is that her trade was made earlier. When she first pushed off to start the spin, she pushed against the ice, and the ice belongs to the enormous Earth beneath it. Her modest twirl was paid for right there, absorbed into a planet so vast that the change is far too small for any instrument to measure. The entry was made. It simply landed somewhere with very deep pockets. And the newborn solar system made its trades too, on a scale that leaves a mark you can still see today. As our cloud fell inward and spun up, its innermost regions could only whirl faster, because spin was being carried outward, passed from the material falling in to the material staying behind. Through the twisting grip of magnetic fields and the slow friction of the swirling disk, great quantities of gas were flung away entirely in winds and jets, leaving the young system altogether and taking their share of the turning with them. Here is the trace that leaves. The Sun holds more than 99% of the solar system's mass, but it does not hold anywhere near that share of the system's turning. Most of the angular momentum in our solar system today is carried by the planets, out in their wide, slow orbits, and Jupiter alone accounts for the bulk of it. The Sun kept nearly all the material and gave away most of the motion, braked in its youth by its own magnetic winds. Sit with the strangeness of that for a moment, because it is one of the quiet oddities of our home. The crumbs got the motion. Follow that logic outward, and a realization arrives. The universe is not simply full of things that turn. It is full of exchanges, transfers, and settlements reaching back through every collapse and collision since the beginning. Turbulent clouds seethe with swirls in every direction, most of them offsetting one another. Galaxies talk their neighbors one way and are talked back the other. Every act of turning was, somewhere in its own system, an act of trading. Let the accounts settle themselves. They are good at it, and now the deepest layer, kept for last because it is the strangest, and because by now your thoughts are soft enough for it to simply drift past without needing to be caught. You might imagine that far enough down, in the quiet of the atoms, the turning finally stops. It does not. In the 1920s, physicists studying the light given off by atoms discovered that their measurements only made sense if the electron itself carried angular momentum, built-in, permanent, unremovable. They called it spin, and the name is slightly mischievous, because an electron is not a tiny ball rotating in any ordinary way. As far as an experiment can tell, it has no size to rotate at all. Its spin is something deeper, a fixed intrinsic quantity that the particle simply has, the way it has charge, the way it has mass. It cannot be sped up, or slowed down, or taken away. Every electron in your body carries exactly the same eternal portion. So do the quarks inside every proton. Even light carries it. Every photon crossing your window tonight bears its own small, fixed measure of angular momentum, and laboratories routinely put that to work, twirling microscopic objects with nothing but a beam. But do not let that fact whisper the wrong lesson, because there is a tempting one nearby. Intrinsic spin obeys the same bookkeeping as everything else. In many atoms and many materials, electrons pair up with their spins opposed, and those contributions cancel, adding to nothing at all. Other atoms and particles keep a total that is not zero. Quantum spin can balance. It does not always do so, and that is exactly the point worth carrying, because it means stillness, in the sense of a perfectly balanced total, is not forbidden anywhere in this universe. It is ordinary, It is all around you, in the quiet, paired electrons of your blanket and your walls. There is no law anywhere in physics that says a thing must turn. So here, at last, is the honest answer to the question this whole journey was named for. And I think it is better than the myth would have been. Why does so much of the universe spin? Strictly speaking, not everything does. Some things sit balanced. Some worlds have been braked almost to stillness. There is no cosmic rule forbidding rest. What there is instead is a universe that was born busy. Matter came together in crowds, in turbulent clouds and colliding streams and crowded young systems, where every off-center tug and glancing collision handed out, turning freely in every direction. Always paid for somewhere, always by trade. And then gravity gathered those crowds inward, and the skater's law amplified whatever each gathering happened to be holding, concentrating faint whispers into days and seasons and storms and pulsars. Nearly everything turns, not because stillness is impossible, but because the history that built things was full of exchanges, and the turning handed out in those exchanges cannot be thrown away. It can only be passed along, traded, carried off, or balanced somewhere else. Angular momentum, once acquired, is never simply forgotten. It changes hands. The universe does not forbid stillness. It simply remembers every turn it is given. That is the whole answer. And notice what kind of answer it is. Not a decree, a ledger, kept faithfully, in every system, for 13.8 billion years. Nothing in that ledger has your name on a debt. Every entry concerning you was settled long ago, in clouds you never saw, by collisions you never felt. You arrived long after the bookkeeping was done, free to simply ride what remains, and with the question answered. There is nothing left tonight that needs thinking about. The ideas can be set down now, one at a time, like tools at the end of a workday. There is only one place left to go, and it is not out among the stars. We have been out there all night. Come back now, gently, back from the wheeling galaxies, past the ticking lighthouses of dead stars, past the great striped storms of Jupiter and the golden clouds of Venus, back across the quiet miles, to a planet with one moon, to a continent, to a town, to a building with a roof, to a dark room. To you, nothing here has changed while we were away. The pillow is where you left it. The walls are keeping their patient watch. The room still feels perfectly, deeply still, exactly as it did when we began, before you knew what the stillness was hiding. But you know now. So let us feel it one last time, with everything the night has taught you, not as a lesson, just as a lullaby. The ground beneath your bed is turning eastward, smooth and silent, carrying you through the darkness at hundreds of miles per hour. It has been turning this way, without pause, since long before there was anyone here to carry. It was turning under the dinosaurs, whose days were shorter than yours. It was turning under every person who ever lay awake wondering about anything at all. Somewhere above your roof, the moon is holding its familiar face toward you, the same face it held toward the very first creature that ever slept. It is drifting an inch and a half farther away this year, gentle as a long goodbye that never needs to finish. The tides it raises are crossing the oceans right now, unhurried and exactly on schedule, quietly trading our spin for its distance the way they have for 4 billion years. And the turning you are riding is old. Older than the ground itself. It began as a whisper in a cloud that no longer exists. A drift so faint that nothing could have noticed it. In a place where there was no sun yet, and no earth, and no morning. And the cloud fell. The way clouds fall. And the whisper was amplified into a disk. And the disk became worlds. And one of those worlds became this one. That whisper is still here. Underneath you, carrying your bed toward morning at this very moment. When light comes through your window in a few hours, that will be the whisper arriving. Dawn is the oldest heirloom you own. You do not need to hold on to any of it. That was never the arrangement. The earth does not require your attention in order to turn. The ledger does not need you awake in order to balance. The galaxy will carry the sun, and the sun will carry the earth, and the earth will carry you all night, every night, whether you are awake to know it or deep asleep and dreaming of nothing at all. Of all the facts we gathered tonight, that one is the softest. The spinning universe is the one thing in your life that never, ever needs anything from you. So let the last of the day loosen its grip now. Whatever went unfinished today will still be there tomorrow. And tomorrow will arrive on its own, delivered by the turning, exactly the way it always has been. Every person you have ever loved, every place you have ever been, every morning you have ever woken into, all of it has been riding this same quiet carousel alongside you the entire time. No one you know has ever been still. No one you know has ever fallen off. Your shoulders can let go of their last small weight. Your breathing can find the pace it keeps when nobody is listening. The room is dark, and the planet is turning it slowly through the night, like a hand rocking a cradle, the way it has rocked every sleeper who ever lived. You are not lying still tonight. You are being carried. And that is where our journey rests. Let every number from tonight drift loose now, the miles per hour, the galactic years, the 700 turns in a single second. None of it needs to survive until morning. If anything stays, let it be small and simple. The stillness you feel is a smooth ride, not a stopped one. The spin all around you is a memory, older than the sun, faithfully kept, and every turn in the universe was part of an exchange, settled somewhere long ago, asking nothing further from anyone, somewhere out there right now. A storm wider than our whole planet is finishing another year of its long red turning. A city-sized star is sweeping its lighthouse beam across the dark, hundreds of times in the space of your next breath. The moon is easing an inch and a half farther out, taking with it a fraction of a second of some future day. And, underneath all of it, the same patient law is holding. Everywhere, the one you now carry with you, the one that turned a bedtime question into a night among the stars. If these slow journeys through the universe help your nights end more gently, you are welcome to travel with this channel again. Leaving a like or subscribing tells us these quiet hours are worth making, and helps another tired mind find their way here some night. Only if you wish. Nothing tonight ends differently either way. The earth will keep turning while you sleep. It is very good at that. It has been delivering mornings for more than 4 billion years. And it will not miss yours. Good night. Sleep deeply. And let the world carry you until the light comes around again.